Hello, how are y'all doing?
Good, how are you?
Doing okay. And I can even hear you, so that's a good thing. Oh, okay. So I believe I have everyone exam graded. I'm happy with the results. But like at least one of you has noticed, I may make mistakes in my calculation of your answers. So if you discover something that you think is an error, please let me know and I'll go and I'll look it over. And if it's an obvious mistake that I made, we'll do a quick fix. So there's one thing I wanted to mention. And second thing is I believe it's likely that on Thursday I will need to have office hours at the earlier of the two time slots, like right before class or right after class. Today is Wednesday, at the same time as today is likely when office hours will be 3:25 till 3:50 p.m. Okay. So that's things I want to mention. I haven't put that online just yet. And I think we're sort of heading towards the last week of classes, so that's pretty good. Uh, Someone asked me earlier today a good question, so I wanted to repeat the question so y'all can hear it. The question is, hey, tell me more about what's going to be on the final. Geez, I guess it's coming up soon, a week from tomorrow. And the final exam should be about 50% longer than either of our two midterms. It'll be on paper, in person. But maybe the most important thing to remember is while it's 50% longer, you'll have about twice as much time to do the exam. So there'll be more time for questions. So if you felt rushed for time, it's likely that you will feel less rushed for time on the final. That's one thing. Second thing I want to mention is the distribution of points. If you will, think there's three chunks of material for the course before midterm one, between the two midterms, and then since midterm two. The since midterm two content should be about two-thirds of the points on the final exam. And then the other third should be from maybe a sixth for each, the before midterm one or between the two midterms. So that's approximately a way of thinking about it. So with that in mind, prep yourself appropriately, and that's it for administrative announcements that I would want to make. Do any of you have questions relating to administrative things that you'd like addressed or commented on?
So for the final, how many sheets of paper for equations are we allowed to have?
8.5 by 11, one piece, both sides.
Okay.
Uh, and there's no limitation on the font size. If you wanted to type it out, I wouldn't recommend that. But yeah, literally, you could probably do work with an iPad, and you know how you can expand and make things big and then shrink it down. I'm sure you could manage to get absolutely everything you really feel you need to have written down, either by definition or sort of by way of example, that you wouldn't already remember. So if you go through the questions, what do I likely need to know and what do I think I already do know? Well, sort of those will both tell you between those two questions answers what should be on your note sheet. So yeah, most people are pretty happy with 8.5 by 11 both sides. If you find yourself just as someone who writes really big, I would encourage you to sort of do your best to find a copier where you could take two pages side by side, put them down, and shrink it down to one page. It's not exactly European paper like A4 where it's easy to do that, but it's close enough. And so I'm sure you can manage to get it 8.5 by 11 both sides. So that's that really long-winded answer to your question. Sorry, Meg. Anyone else? Okay. So what I'd love to do is to get into content that's, in my opinion, new-ish. Okay. And Wednesday and Thursday, like always, there's the set of things that we have from the past, notes from past terms. Okay. Past video from 2 years ago, covering the same content as today, approximately. Okay. And then the topics for the day is like I need to dot an I and cross a T. That was literally a joke. I'm gonna sort of adjust the t-test. I'm going to mention this thing called the pooled t-test, and then we'll talk about using a t-based confidence interval for paired data. Then we're going to talk about the logic of hypothesis testing and hypothesis testing to about one mean, and then to compare two means to each other. And that's probably where we're going to emphasize sort of 8.2, and then the lab definitely emphasizes 8.2. So with no further ado, I want to mention that this thing exists called a pooled t-test. Okay, let's talk about what the heck that is. Versus the t-test that I introduced in class. Actually, I think the authors of our book introduced the pooled t-test first. It's a procedure that statisticians rarely use. Not a t-test, a t-confidence interval. There we go. Confidence. A pooled T procedure, if you will, is something that statisticians very rarely use in the context of two populations where you want to compare the population means. And again, t-test, we have to have a normal population or a large sample size. So I'm going to draw it looking approximately normal, but you think maybe a large sample size would be fine. Mu1, mu2. Our authors note that if you have the same standard deviation sigma in each of the two populations, there's a slightly narrower, I guess more precise, confidence interval that we could utilize. The pooled T procedure estimates that one unknown population standard deviation common to both groups by effectively, I'm going to averaging the variances, the sample variances from each of the two groups according to the sample sizes, and then taking a root. And if you indeed believe that your two populations have an identical population variance, the pooled T procedure is the right way to go. Okay. And the benefit is you will have a slightly narrower confidence interval. How much narrower is it? So darn rare. Okay. Let's see if I could bring up an example, and we'll see how little of a difference it makes. Okay, there we go. And maybe clear this. And okay, so yeah, you dealt with yesterday the Finch data, and it was named Bumpus. Okay. So we've got our finches that died and the finches that survived. And let's suppose I want to care about the weights of the two birds, and I want confidence interval for how much heavier are the birds who survived than the birds that died. You learned, yeah, fit Y by X. Okay. So is the weight, or how different is the weight between the two groups? Click OK. And yeah, indeed, we have this T-based procedure. My confidence interval is that the birds that survived are 0.37 to 1.55 grams heavier on average than the birds that died. Okay, literally, mu survived minus mu died. We are 95% sure that it's in the range, I'm sorry, 0.07 to 1.55. So that's how wide it is. Yeah, it's like a 1.48 units wide. If I were to turn on the pooled T procedure that assumes that the standard deviation are really the same in the dying and the surviving birds, my pooled T procedure, okay, looks exactly the same, except for the confidence intervals a little narrower. It's like 0.096 to 1.53. So just like I said, a hair narrower. Is it worth it? Is it the right way to go? I'm not going to tell you. I'm just going to say that I and most statisticians I know will rarely use that pooled T procedure when we indeed have the opportunity to use the regular T procedure. The gain is small, but it comes at the cost of assuming something that might indeed be false. It's probably safer to go with the slightly more conservative approach, the slightly wider confidence interval. The reason I believe, and I should chat with the authors of our book about this sometime, but the reason I believe that we tend to, as statisticians, put the pooled procedure into books is one, there's some business major out there, or maybe some business faculty member or a faculty member in engineering who said, I learned that when I was in grad school, so I want my students to know it. Okay. Or perhaps the idea of pooling two standard deviations, averaging their squared values according to the sample sizes, that's a cool idea. The idea that we really have one common standard deviation and we've got two separate ways of estimating it. Well, naturally, estimating the unknown one population value with the two data sets, that's sort of a cool idea. And so authors, I should check with them to see what their motivation was. I have the feeling it's the first, but the second might be good as well. So that's one of the dots, I's that I wanted to dot, or the T that I want to cross is now a confidence interval for paired data. So maybe that's also best done within the context of an example. So let's grab an example data set, and the one I wanted to use was sunscreen. Okay, so sunscreen tolerance. So SU for sunscreen tolerance. Okay, there we go. Here we've got data on a collection of individuals and how long they were able to remain in the sun before noticeable sun damage occurred. This one individual, they literally had the control sunscreen applied, and at 30-minute mark in a tanning bed, we said, "Oh, dude, like you could press on the person's skin and you say, oh yeah, you sun damage." We measured and we noticed some noticeable damage from the sun. And so we said, okay, get out of the tanning bed. We are going to mark you at 30. That same person with their other arm, they were wearing actual sunscreen. Okay. And we measured it there, and they were able to remain in the tanning bed with that arm for 120 minutes, like 4 times as long. Okay. And I don't want to emphasize the ratio. I want to talk about how many more minutes. That's a 90-minute gain between the one arm and then the other arm. Okay. So each person, and there are 13 people here in our data set, each person gives us two readings, if you will, a before and an after, with the sunscreen, without the sunscreen. And the real key is you have not two means that we're trying to estimate the difference of, but we were trying to estimate the mean of the differences. Let me say that again. Rather than estimating the difference of two means, we're estimating the mean of a collection of differences. Conceptually, it's something like this. Instead of a group of individuals with sunscreen and with control, instead of like testing their arms separately, okay, we're going to say we've got a collection of people. It's not like that, but we've got a collection of people who have two arms. And we're going to randomly flip a coin to figure out whether it's the left arm or the right arm that gets the sunscreen, and then the other arm that gets the control. But you get two scores per individual. There's the Y with the sunscreen and Y with the control lotion, no sunscreen whatsoever. Let's make that pencil a little bit narrower so I can read it more easily. And we've got a collection of individuals, all of whom have Y for sunscreen and Y for the control group. And we're going to sample a collection of individuals from that population. And for each person in the sample size N, or better yet, ND is the number of differences that we have. We've got Y bar I is Y from the sunscreen for I, minus Y for the control lotion person I. And indeed, instead of YI, let's call that DI. Maybe that's a little bit cleaner. We've got the difference from that ith individual. Okay. And we get a D bar, an average of the differences, a standard deviation of the differences, and we know the number of differences you have. And so our procedure to estimate mu of the differences boils down to exactly what you'd expect it to be. Okay. You're going to estimate mu of the differences with D bar. a 100 times 1 minus alpha percent confidence interval, think 95% confidence interval for mu d. And that corresponds to how much longer you can be in the sun before sun damage occurs if you have sunscreen on than if you don't. Okay, that's going to be d bar, the average of the differences, plus or minus t alpha over 2 in that upper tail area, and then degrees of freedom equal to nd minus 1 times then the standard deviation of the differences over the root of nd, the number of differences. So our equation looks a lot like the one we talked about just 2 class sessions ago. Remember when we said x bar plus or minus z alpha over 2 times the SD over root of ND? And then we yesterday said, well, what if we don't have a known standard deviation, but instead we use a sample-based standard deviation? You would replace that T or Z with a T. Okay, that was yesterday. Our equation looks exactly like before. You already know the method. The method is just find the differences first. And then once you have the differences, go ahead and treat them as though they're one sample of differences that you'd like to know the population mean of. So inside GMP, it's pretty straightforward. If you have the data organized in this fashion, and let's pull open GMP, if you have them organized in this way, and the data literally is required to be in 2 separate columns, a before and an after, if you will, a control and a sunscreen, and each individual is giving me 2 scores, one for each the control and the sunscreen. Under analyze, we're going to go with analyze specialized modeling, matched pairs. So again, analyze, yeah, we're going to analyze this data. Haha, it's not the regular thing that we do, like fit y by x. Okay. Okay. And so it's something specialized. Oh, I've got pairs of data. I've got a before and an after. I've got a left arm and a right arm. Yeah, I've got matched pair data. And just tell me where the response values lie. They're in both the control and the sunscreen. And I'm going to drag it control and sunscreen, control first, sunscreen second. If we put them in the other order, it's going to look similar. But I'm finding out that mu, I get the whole procedure shown. I don't love the graph here without the explanation for it. I'm going to say I want to focus on the average of the differences is 248 minutes. The upper end of the confidence interval for mu sunscreen minus mu control is 302 minutes. The lower end is 194 minutes. And so that's 3 hours, 15 minutes, up to 5 hours. With sunscreen, people can remain on average in the sun 3 hours, 15 minutes to 5 hours longer. That's pretty good information. Okay. Someone will always ask, why are we doing this instead of the other method, the method that assumes independent samples? You don't have independent samples. That's the answer. You've got naturally some people that are darkly complected and might take longer to be receiving sun damage, whether they have the sunscreen or control. And then other people are very light skinned, and so they're going to get sun damage very quickly, whether they're using sunscreen or the control lotion. Yeah, literally, you want to give them a control lotion. Yeah, you want to have the people just wipe something on their arm, because otherwise they know which arm doesn't get the sunscreen, and the knowledge might impact in some strange biological way. It might impact the time till damage occurs. I don't believe it's likely, but I've seen weirder things. So control lotion and then the sunscreen, separate arms, same person. And there would likely be a correlation, and I'm going to make emphasize it with the graph builder, that the sunscreen amount of time until sun damage occurs is probably predictable based on the control lotion amount of time until damage occurs. Maybe if we're trying to draw a trend line in, or even not having the trend line, you would say if you're with a control lotion able to stay in the sun longer before damage occurs, you're also likely going to be able to remain in the sun longer with the sunscreen. The positive correlation here is what causes our confidence interval for the mean of the differences to be narrower than if we were calculating a confidence interval for the difference of the two means. There's a bit of a subtlety there, but you might say, cool, I'm happy with that. Move on. I want to pause though for a moment and say, do any of you have questions on the t-based confidence interval for differences? Okay, so what I'd love to do then is to switch gears and say, well, where are we? Where we're going today? We've got one more thing that we're going to do is talk about hypothesis testing. And then I'm going to sort of show you two separate hypothesis tests. Okay. One is for one mean and the other is for two means. And I'm going to sort of just speak as though we have a large sample size. And you should know in the context of the lab that if you have a large sample size, or if you have normal populations that you're sampling from, the methods that we're going to describe today are absolutely a-okay. Okay. Here we go. Let's talk about the one sample case. And we want to infer something or learn something about the population mean. Okay. So there's a distribution out there, and I'm going to draw it as though it's normal, or maybe we could get away with a large sample size. Okay, either way is fine. But there is a number out there called mu, another number out there called sigma, and I'm going to take a sample size n, and I get x bar or x1, x2, all the way up through xn, giving me x bar and s, the standard deviation of my sample. Okay. So this is the context of where we're at. This is just like we've dealt with before. And we're going to start from a probability statement like we did when developing the confidence interval. I said the probability that and I'm going to go with minus t alpha over 2 less than or equal to x bar minus mu over s over root of n less than or equal to t alpha over 2. That is 1 minus alpha. Okay. If you're thinking conceptually, if you took a standard deviation and a mean, okay, and if you knew mu, okay, then the distribution of x bar, well, subtract out the mu that you know and divide through by what we've been terming the standard error. If we took the difference of our sample mean and the mean of the population that I'm sampling from, divide through by the standard error, that would follow a t distribution, okay? And 1 minus alpha is the chance that you're in the middle. Alpha over 2 is the chance that you're in either of the two tails. And because we're using a t distribution, because we use S instead of the unknown sigma here, from T alpha over 2 and up, and negative T alpha over 2 and down. Those are each areas alpha over 2. So that's the probability statement. Does that tell us anything about the actual value of mu? You would estimate mu with x bar, and we have a confidence interval, but we haven't tackled the question about could it be that this is the actual population mean mu? Let's suppose we took a random sample of students from Cal Poly and measured their IQs. I might want to know, are Cal Poly students average with regard to IQ or not? I'm specifying two hypotheses. One we'll call the null hypothesis, one we'll call the alternative hypothesis, H0. Null hypothesis, A for alternative, the alternative hypothesis. I could say the specified value, the true value for mu is just some fixed mu naught mu according to the null hypothesis. Or my alternative could be that mu naught, mu naught. That was funny because it's mu is not equal to mu naught, but you could abbreviate it mu naught, mu naught. Mu is not mu naught. Okay, I thought it was funnier than you did, but of course, this is one of those silent classes, so who knows? So these are two statements about reality, and one of them is true. The null and the alternative hypotheses are logical opposites. But we want to come up with a way of measuring how closely the data match up to the null hypothesis. And if that measurement with our sample mean says, yeah, we could have easily seen the sample mean we did see if the null hypothesis had been true, you want to stick with the null hypothesis. There's no reason to doubt it. We think about this sort of like Law and Order, the TV show. The criminals assumed to be innocent, or the perpetrator, the person accused is assumed to be innocent until proven guilty. You're going to stick with the null hypothesis until you're convinced by the data that it's wrong. Sort of like the scientific method. We're going to stick with our old understanding of reality unless we see data that says the old belief is clearly incorrect, in which case we have to adopt a new belief. In any hypothesis test, there's a few parts to the hypothesis test. Those parts, and different books will have different numbers of parts to a hypothesis test. I'm just going to tell you that it's, yeah, I'm just going to say, here's what I like to say, but I don't argue with people who count differently than I do. One is the hypotheses. Okay. And so part number one is the null hypothesis. Part number two, the way I phrase it, is the alternative hypothesis. A statement about mu, because we're talking about a hypothesis test for one population mean mu. Three is a test statistic. And the way I like to define a test statistic is a way of measuring of how close our data are, to what you'd expect to see if the null hypothesis is true. Okay, so basically we're saying, yeah, what did we see, and is it close to what we should have seen? And so let's think about in the context of our example. Well, the average IQ of Cal Poly students is perhaps 100. On the other hand, mu might not equal to that value of 100. And if my sample mean was like 140, I think I'm not going to believe the null hypothesis. If my sample mean was 108, I might still be willing to stick with the null hypothesis. Again, the null hypothesis is what you're saying you're going to stick with until you're convinced by the data that it's wrong. And the test statistic is just a way of measuring how close the data is to the null hypothesis. Okay, so let's give you the test statistic we would use in the context of one sample mean from one population, I guess a simple random sample, okay? My test statistic is T, okay? The T test, if you will. It's literally like X bar minus our hypothetical mu naught divided by S over the root of N. Okay, there's your test statistic. And let's give you a hypothetical. What if our sample average IQ in Cal Poly students that we sampled was 120, but we should be seeing 100. If y'all were really average, we should see IQs clocking in about 100. If it was 120 that we saw, the standard deviation 15, and we've got the root of the sample size, and I'm going to go with the sample size for mathematical convenience. Geez. let's go with okay, so I don't know if I'm going to be able to pull it off, but with 100 I could. Okay, so 100 data points. Okay, and so root 100 is easy to calculate. And a root 100 would be 10. And so we've got 20 upstairs over then 15 over root 100. That's 1.5. And that is huge. How many times does 1.5 go into 20? A lot. So if one of you would calculate that for me, I'd love it.
80 if I had to guess.
80?
Because
I'm going to go with 20 over 1.5. 8 maybe, but I'm
13.3.
yeah, 13. Thank you. And I'm going to go with, yeah, 13.3. Probably I could be more precise than that. I would in general love to be more precise than 13.3, but right now, not going to do it. Third thing that you need in a hypothesis test is a calculation of what we'll term, actually a fourth thing, the p-value. And the p-value is literally equal to the chance of observing a result at least as extreme if the null hypothesis is true. And I apologize in that lower right corner. Let me repeat it again and go slowly. The p-value is a chance. It's the chance of what? It's the chance of seeing a result that is, underlining in orange, the probability of seeing a result at least as unusual as what we did see if the null hypothesis really, in fact, were true. We're going to ask ourselves a hypothetical. Could I have seen a sample mean of 120 if the population mean was only 100? That's a great question. Could I have done that? The answer is, we'll see how likely that is. The p-value is indeed that chance. So what I'm going to do is grab this now and do a screenshot, clear this unless you have a question first. Okay. So what I'm going to do then is go into calculating that p-value. The p-value is indeed the area from 13.3 and up, or a negative 13.3 and down. Notice that our alternative hypothesis is that it's just not 100. So I guess a sample mean of 80 would have been just as unusual if the population mean were 100 as if the sample mean were 120. So either way, unusual, more extreme, is the same in this case. And I guess we need to know only one thing for this t distribution, degrees of freedom would be n minus 1, in this case 99. So let's pull open our probability distribution table, and maybe I'm going to use the t table because that way we can sort of get ready for the final exam where you're not going to have that probability distribution calculator tool. I'm going to look at the t table. Okay. And I find that if I have the right degrees of freedom and we had 99 degrees of freedom, I'm going to use this 60 degree of freedom row. So I know that somewhere in this range is a value that's helpful. And my t value itself is in this range, well, except for it's not really, it's to the right of even the largest t value, 3.460. And so if I were to go up to the top, I know that the lower tail shaded area is 99.95, meaning the upper tail shaded area that I'm caring about from my 13.3 and up, that's going to be less than 0.0005. This tail shaded area is less than 5 in 10,000. And so my test statistic where I've got 13.3, my lower tail area is less than, I'm sorry, upper tail area is less than 0.0005. And my lower tail area is also less than 0.0005. 5, my p-value has to be less than 0.001. Okay, so step 4 complete. We get a p-value. Okay, finding an area. The software will usually give you a p-value, so you don't have to worry about this too much in the context of comparing two means. But yeah, if you are doing it by hand, you could do it this way. Then the last step in a hypothesis test, step 5, V, is hit a conclusion. Tell me whether you believe the null hypothesis still, or whether you've been convinced by the data that the alternative is better. The bland way that we would say it is something like either we reject the null hypothesis, or we don't yet reject the null hypothesis. Okay, so it's one of these two conclusions. When should you hit which conclusion? That seems like, well, shouldn't the test statistic, which measures how closely the data match the null, shouldn't that help us? Yes, it does, because it gets us to the p-value. We reject the null hypothesis if the p-value is less than alpha 0.05, in general alpha, a specified rate of error, or greater than or equal to that 0.05. So if your p-value is like 0.0001 or even smaller, like we found, you would reject the null hypothesis. You'd say, I've seen evidence in the data that I don't believe the null hypothesis anymore. If we were to believe the null hypothesis, the laws of probability just said we saw something freakishly unlikely. Would you rather believe that the null is true and you were a freakishly unlucky person, like win the lottery tonight, lucky, yeah? Or would you rather believe that, nah, the null hypothesis, we don't believe that? Doubt the null or believe it and believe that you were just really unlucky. Small p-values say believe the alternative. Any questions about that hypothesis testing procedure? Okay, so what I want to do is get towards then the last method of the day. And it's the one that we use more often than the hypothesis test about one population mean. Admittedly, engineers do hypothesis testing about one population mean more than any other group of people do. But more often than not, you'll find yourselves comparing two situations, if you will, two populations. Again, I'm drawing a normal population as though that's true. There is a mean mu1 in population 1 and a standard deviation sigma 1, a mean mu2 in population 2 and a standard deviation sigma 2. We're going to take a sample size n1 from population 1, sample size n2 from population 2, and we're going to get x bar for group 1, and S1 for this first standard deviation, and then X bar for group 2 and S2 for the second group's standard deviation. And more often than not, we want to test the hypothesis that the two means are the same. The two means are identical. Okay. So I'm going to state the null hypothesis, and I'm going to state it in a way that allows me to broaden that later on. But my null hypothesis is that mu1 minus mu2 is a specified difference. I'm going to call that delta. Usually, delta is 0. And if mu1 minus mu2 is 0, maybe I should call delta 0 according to the null hypothesis. And usually delta is 0. And so if we reject the null hypothesis that the difference of the means is 0, we're saying that the means are different from each other. The alternative hypothesis, well, there's actually not just one alternative that we could use. There's 3 possible alternative hypotheses. And I'm going to put them in this order. Mu1 minus mu2 is greater than delta 0, or maybe mu1 minus mu2 is less than delta 0, or mu1 minus mu2 is not equal to delta 0. The plain English way that a person might rarely phrase this is mu1 greater than mu2? The question is mu1 greater than mu2 corresponds to an alternative hypothesis that mu1 minus mu2 is greater than 0. Is mu1 less than mu2? That's going to correspond to an alternative hypothesis that mu1 minus mu2 is less than 0. Or is mu1 equal to mu2 or not? The not case corresponds to the difference of the means is not equal to 0. So there's these three possible alternatives. The first two we're going to call directional. Alternative hypotheses. Non-directional. Is corresponding to the not equal to alternative. Because, yeah, literally, like with the IQ example earlier, a sample mean of 120 is just as far away from 100 as 80 is from 100. We don't really care if the two means are different from each other in the positive way or in the negative way, just that they are differing from each other. So I'm not going to show you a pooled t-test. If you want to do the pooled thing, you could read the book by yourself on that one. No one ever does pooled. I shouldn't lie. Rarely should a person ever use a pooled t procedure. Null and alternative hypotheses, first two steps. Third step is the test statistic. Our test statistic is t. And I'm going to say just x bar 1 minus x bar 2. That's what the data are wanting to say. And from that, we're going to subtract delta 0, the hypothetical population mean difference. Yeah, literally mu1 minus mu2 according to the null hypothesis. That's what we're going to compare our difference of sample means to. And we're going to say that difference is relative to the standard deviation of group 1 and the sample size of group 1, and also the standard deviation of group 2 and the sample size of group 2. This denominator here, I'll put within a green parenthesis, that is itself the standard error for the difference of the sample means. Yeah, it's a number that we already looked at in the context of a two-sample t-based confidence interval. It tells us how close x bar 1 minus x bar 2 tends to be to mu1 minus mu2 in reality. So in this test statistic, we're comparing what the data saw, what the data are telling us, to what the null hypothesis says we should likely see, and divide that through by the typical value of how close x bar 1 minus x bar 2 tends to be to the truth. And so this t number tends to be sort of like a normal curve. So I think normal rules apply to t approximately. If we saw a normal value outside the negative to positive 2 range, you'd say that's unusual. Similarly, if a t statistic is outside the plus or minus 2 range, that would be unusual. That would be with a low p-value. So let me show you last where you're going to spot inside GMP. If you're doing it not by hand, but with the software, where you're going to spot inside JMP these output. And let's clear that. And let's go back to our example from the other day, the catfish. We've got those data queued up, I think, catfish. And again, we have, remember, the white and the flathead are all sort of like zeroed out, okay? We've only got the blue and the channel catfish. My question is, well, okay, my question for yesterday was, hey, how much longer are the blue catfish than the channel catfish? We're not asking how much longer anymore. That's a confidence interval question. We're now asking, is the average length of blue catfish equal to the average length of channel catfish? Different question. They're sort of related, but they are literally different questions. Yes, no questions go with hypothesis testing. And under analyze fit y by x, we'll be able to tackle the question about the length. Is the length different between our two species that we're considering? Is the length different between the two species? That's a hypothesis testing question. I click OK. And I get the same result as we had yesterday. Our graph here looks sort of like these two weirdly shaped musical instruments. And you'd say, yeah, this mean seems to be a little bit lower or higher than this one because of all these unusual values. If we turn on not the pooled, but the t-test, we then get not just the confidence interval for how much larger the channel, the blue catfish are than the channel. We've got a test statistic, that T ratio here, that negative 5.16. That is the value that you would get when doing it by hand. The equation we just gave you is right there. I'm going to show you in a second how to get that by hand if you wanted to, but our test statistic is negative 5.16. And for the alternative hypothesis that there's a difference in the two population means, your p-value is less than 0001. For the alternative hypothesis that blue catfish have a higher mean than channel catfish, remember blue is subtracted from channel, that's going to be a negative. That p-value is also less than 0001. We would believe the alternative hypothesis. Let's go ahead and see one other thing that would allow us to get the result by hand. These means and standard deviations, if I tell you the sample size n, the mean and the standard deviation, we should be able to get the equation. So what I'm going to do is sort of move this over here so I can see everything I need right there. The test statistic T. Hold on a second. Yeah, my test statistic T, and okay, here we go. My test statistic T is, again, the difference of x bar 1 and x bar 2 minus the hypothetical population difference, 0, over then our root of S1 squared over N1 plus S2 squared over N2. So let's figure out which is group 1 and which is group 2. I usually recommend, if there's any doubt, just go with the larger sample mean to be group 1. This is not what our software did for us, but we could do what we want. So I'm going to have 347.4 minus 321.3 minus 0. Again, we're comparing the difference in the sample means to a hypothetical no difference in the population means. Okay. Divide that through by, well, geez, we're going to have to sort of do a little bit of extra calculation here. The first group standard deviation, 186.73 squared over 2644. And then the second group standard deviation, 99.43 squared over the second group sample size, 801. And that should be equal to, ultimately, the same thing as our test statistic T, negative 5.16 gave us, except for because we put the terms in the other order, I'm going to say 5.16. Okay, so p-value, you get it for free. You know what you're going to believe. You're going to believe that blue catfish are longer on average than the channel catfish. Because why? Well, if they weren't longer on average, then I would about never see results like I did see here. We shouldn't have seen what we did see if the null was true. Don't believe the null if your p-value is low. Okay, like before, I'm noting it's about time to be done for the day. And so I'm going to say, I'm going to stop the share and hang out for a little bit. If you have any questions, I'm happy to answer them. But I am stopping the recording now, unless you tell me you want me to not.